welcome back everyone to the YOLO series. In the last 3 videos, we have seen about all of the concepts mentioned in the YOLOv3 and YOLOv4 paper. But honestly, we have discussed a lot of points and it's very difficult for you to wrap your head around all of these concepts. So the purpose of this video is to summarize all of the interesting points from these 2 papers and compare the 2 models side by side so that you can understand and identify the differences between the 2 models. So we're going to put it all together and we're going to see the architecture of YOLOv3 and YOLOv4 in this video. So first, let's see a summary table which is going to show us all of the interesting points covered in the last 3 videos. So let's see the YOLOv3 and YOLOv4 model side by side in this table. For the backbone, we used darknet 53 in YOLOv3, and we used CSP darknet 53 in YOLOv4, which is a modification of the original backbone by adding a CSP architecture, and we will see this in detail on the next slide. On the neck part of the network, a feature pyramid network was used in YOLOv3 and a path aggregation network plus an additional spatial pyramid pooling was used in YOLOv4. On the head part of the network, both YOLOv3 and YOLOv4 use the same kind of method, and we will see this in detail on the next slide. So in terms of activation functions, all of the layers or the convolutional blocks used a leaky ReLU in YOLOv3, but in YOLOv4, some part of the architecture used the leaky ReLU and some of the blocks used the mesh activation function. In terms of calculating the regression loss in order to find the predicted bounding boxes, the mean squared error loss was used in YOLOv3 and the CIOU loss was used in YOLOv4, and we have covered the CIOU loss in the YOLOv4 video in detail. So if you want more detail about this kind of loss, you can watch that video. But basically, the mean squared error is trying to identify the difference between the prediction and the target box and squaring the error. In terms of data augmentation, we used a pixel-wise adjustment in YOLOv3, and we used mosaic method in YOLOv4. And in terms of regularization, we used dropout in YOLOv3, and YOLOv4 used drop block, which is a modification of the dropout. So regularization is mainly used in order to make the model avoid overfitting problem. And one way we can do that in the conventional method was to use a dropout method, which eliminates some of the activations in the neurons. And when we do this, we're not doing this spatially, so we're not doing it on the convolutional blocks. So in order to eliminate some of the pixels or the relationships between the pixels in the convolutions, we use a drop block method. And in terms of normalization, we use Bush normalization in YOLOv3. And we have seen in the video about YOLOv4 about cross mini-batch normalization. And in attention module, none of the attention modules were experimented in YOLOv3, and the spatial attention module was used in YOLOv4. If you want more detail about the spatial attention module, you can take a look at the video about YOLOv4, where I cover in detail about the spatial attention module and the channel attention module. And in terms of the loss function trick, none of the loss function tricks were used in YOLOv3, but in YOLOv4 we used class label smoothing and grid sensitivity. Now let's see the overall architecture of YOLOv3 by putting it all together, by putting all the concepts that we have covered in YOLOv3 video, and let's compare them side by side. So we're going to start with an input of 416 by 416 by 3, which is going to be the image. So this is the image width, height, and number of channels. And the first block will be a convolutional block, and it's going to contain a convolution, batch normalization, and a leaky ReLU. So these three are going to be called CBL. So this is the blue box. And the number of channels will be 32 after the first convolutional block. So here we can see also that we have the first convolution, which is going to be a 3 by 3, and 32 will be the number of channels, and the spatial dimension will be 416 by 416. Then on the second one, we have another convolution, which is going to increase the number of channels to 64, and we're going to have a 3 by 3 kernel with a stride of 2, and whenever we have a stride of 2, we're going to divide the dimension of the image by 2, and we're going to have an image output of 208 by 208. So the rectangles that you see on the left side are going to be the residual blocks, and these are all of the orange boxes. And the X indicates the number of repetitions. So this is going to be one block, one residual block, and sometimes we're going to use multiple residual boxes. So the numbers indicate the number of repetition. So we're going to use this residual block 2 times, 8 times, 8 times, and 4 times. So this is basically the X will be replaced by the number of repetitions. That's why we have res1, res2, res8, and res4. And when we see the residual block in detail, it's going to contain one convolutional block and one residual unit. And residual unit just means we have the input and we divide the input into 2. We're going to send one part of the input into 2 convolutional blocks, which is this CBL, and then we're going to send the other part, and then we're going to add them together after the convolution operation. So we put this residual unit after the first convolutional block, and then we have the residual block. So when you take a look at this unit, it's going to contain one convolution block and one residual unit. That's basically the first convolution that we have seen, which is going to decrease the spatial dimension by 2, is the first convolutional block. And the second residual unit, which contains 2 convolutions, one 1 by 1 and another 3 by 3, and a residual connection, which is going to be this, is representing the residual unit. And the red box, which contains the CBL and res unit, is indicated by the red box. So this res1 represents the red box, and res2 represents the second residual block. And here we also have a stride of 2, which is going to reduce the dimension from 208 to 104. So whenever we want to reduce the spatial dimension of the feature map, we have to use a stride of 2. That's the job of the first convolutional block inside the res block. Then this red box is going to be repeated 2 times. So this is going to be the res2. So we started with an input feature map of 416. Next we're going to have 208, and the next one will be 104. Then we're going to have 2 residual blocks, which are going to be repeated 8 times, and the feature map for the first one will be 52. And after the convolution, we're going to have a feature map of 26, which is represented here. And then finally, for the final residual block, we have a spatial dimension of 13 by 13, and this is going to be repeated 4 times. So this is the backbone of YOLOv3, and this is called Darknet 53. Now, the next part of YOLOv3 will be the feature pyramid network, which is going to be the neck. And here, once we have the output from the last layer of Darknet 53, we're going to perform a convolutional set. And this convolutional set is represented in this box. And it shows 5 convolutional kernels, which are 1 by 1 and 3 by 3. So we're going to use them 2 times, and then finally we're going to add 1 by 1 convolution. And here we can see that we have 5 convolutional set. So that's why we have the times 5 here. So this block is going to represent the convolutional set, and it's similar to the CBL times 5. Once we have this, this is going to be the first head. So these 3 purple boxes are going to represent the head of YOLOv3, and these are going to represent the outputs and where we're going to make the predictions. But before we move on to the head, we have to perform one more convolutional block, which is going to be a 3 by 3 convolution. The CBL here represents the same CBL. Then finally, after performing a 1 by 1 convolution, we're going to predict on the output of 13 by 13. Then once we have the first feature map, we're going to perform a 1 by 1 convolution, 1 CBL, and then we're going to perform upsampling, because since we are going upwards, first we were reducing the spatial dimension. Now we're going to upsample, which means we're going to increase the width and height of the feature map. So when we upsample, it's going to be converted from 13 to 26. And after upsampling and a 1 by 1 convolution, we're going to concatenate with the previous feature map of 26 by 26. So we're going to take this 26 by 26 and concatenate with the one coming from the 13 by 13. The reason that we are performing the upsampling is because we want to concatenate with the same spatial dimension. So the one coming from the Res8 block has a spatial dimension of 26, but the previous one from the first head of the network, it has a 13 by 13. So we want to make them the same spatial dimension so that we can concatenate them. So once the yellow box represents concatenation, and once we finish, we perform another 5 convolutions, which is represented by the convolutional set. And then finally, we do the same thing here. We're going to do a 3 by 3 convolution and a 1 by 1 convolution. And on the 26 by 26 feature map, we're going to perform the prediction, which is going to be our second head. Next, we also do the same thing, and we perform a 1 by 1 convolution, and we do upsampling, increasing the spatial dimension from 26 to 52. And then finally, by taking the feature map of 52 by 52 from the previous block of residual 8, we concatenate with the one which is upsampled from 26, and we concatenate them together. And then finally, we perform another convolutional set. And the convolutional set is going to contain 5 convolutions. And then finally, we perform another 3 by 3 convolution and a 1 by 1 convolution, which is represented here. And then finally, we're going to perform the prediction on the 52 by 52 feature map. So this is basically the YOLOv3 architecture when you put everything together. Now let's see the YOLOv3 head, which was represented by the purple boxes in detail. So the YOLOv3 head performs predictions on 3 feature maps. The first one was a 13 by 13, the second one was 26 by 26, and the third one is 52 by 52. And all of these feature maps, each of the grids on those feature maps are going to predict 3 bounding boxes, which are represented here. And in total, we're going to have 9 bounding boxes from the 3 scales. For the first feature map, we have a spatial dimension or a height and width of 13 by 13, and we have 3 bounding boxes being predicted for each of those 13 cells. And each bounding box has 4 coordinates for the XY position and the width and height, 1 confidence score, and 80 class labels. So in total, these are going to be the predictions that we're going to make on the 13 by 13 feature map. And we also do the same thing for the 26 by 26 feature map. We have 3 bounding boxes, and the rest doesn't change. And here we can see that we are using 9 anchor boxes, and the dimensions for each of the anchor boxes in order to predict the bounding boxes are given in these dimensions on the 13 by 13 feature map. And this is used for predicting large objects, and on the 26 by 26 medium-sized objects, and 52 by 52 is used for predicting small objects, and you can see the anchor boxes used here are very small. Now that we have covered the architecture of YOLOv3, let's put together all of the concepts covered in YOLOv4 in order to form the architecture. And in YOLOv4, we have replaced the darknet 53 from YOLOv3 by the CSP darknet 53. And we start with the inputs of 416 by 416, and 3 will represent the number of channels. And the first one will be a CBM, and CBM just represents a convolution, batch normalization, and mesh activation function. Previously, we have only seen the CBL, and the CBL used a leaky ReLU instead of the mesh activation function. In YOLOv3, we have said that all of the blocks use a leaky ReLU activation function, but in YOLOv4, the mesh activation function was used in some of the blocks, and this block, the yellow one, represents the block, the convolution block that uses a mesh activation function. And the blue box, which uses a leaky ReLU activation function, is represented by the blue box. So once we have the input, then we perform the first convolution, and this is going to increase the number of output features from 3 to 32. And this is also the case in this picture. And then on the first block here, we have the CSP blocks, and that's this one, the CSP part of the name. And a CSP block is represented in this diagram. And when we take a look at the inside of a CSP block, first we divide the input feature into 2. We send the first one into 2 CBMs, which represents a convolution that uses a mesh activation function. Then we're going to use a residual unit, and this residual unit is using 2 CBMs, and then we divide it into 2. After 2 CBMs, we have 1 output, and then we send the first one as it is, and then we add these 2 together. So then finally we add another CBM, and we have the first output from the top, and then we just to directly send the second one, the partial from the input, and then we perform one CBM on the bottom pass, and then we concatenate instead of adding here, and then finally we perform one more CBM, and all of this together represents one CSP block, and the X is just a variable which represents the repetitions. So we're going to use this block repeatedly. So on the first case, we're using it 1 times, so this is 1 times. And for the rest of the cases, we're going to use the first one 2 times, and we're going to use these two blue boxes 8 times, and then the last one will be used 4 times. And when we go downwards, the spatial dimension is being reduced, and the number of output features are increasing. And for the last one, we have 1024. Once we finish the CSP block, then we go to a convolution. Then we're going to perform a CBL instead of a CBM here 3 times. This is represented by 3 convolutions, which uses a leaky ReLU. And then we also introduced a new method known as SPP block. And here we're going to perform some pooling operations using different kernel size of 5, 9, and 13. And we will see this in detail on the next slide. And then finally, after we finish with the SPP layer, we're going to perform another CBL 3 times, which is represented here. And then we are going to concatenate the output from the 3 types of pooling layers, and we're going to send it directly onto the neck of the network. So we have finished the backbone, which is a CSP darknet 53 for YOLOv4, and the next one will be the neck of the network. And in YOLOv3, we used a feature pyramid network, but in the case of YOLOv4, we used a path aggregation network. And we stopped here on the blue box. And here we're going to separate the outputs from this convolution into 2. The first one is going to go on the bottom-up layer. So first we go top down, and then we're going, this is the bottom-up path. On the first bottom-up path, we're going to perform one convolution, one CBL, which uses a leaky ReLU, and then upsampling, up 2D in this case. And here we're upsampling the 13 by 13 to 26 by 26 feature map. And here we also have an output which is coming from the CSP8, which is 26 by 26. And we perform one more convolution, and we reduce the output feature from 512 to 256. And the one coming from here also has 256. And when we concatenate them together, the width and height is the same, and the number of output features will be summed together since we are concatenating, and in total we have 512. And once we finish the first concatenation, then we perform CBL 5 times. This block will be performed 5 times. And then we perform, this is the conv 5 times, and we perform a convolution block CBL and upsampling on the green box. And then when we perform the upsampling on 26 by 26, we have a 52 by 52 feature map. And we take the one from the darknet 53 backbone, which has a width and height of 52 by 52. And we're going to perform a CBL. And This will be 52 by 52, 52 by 52. We concatenate them together, and the output feature is 126, 128, and we sum them together to get the output feature map in the yellow box, which is going to be 256. Once we finish the bottom-up paths, then we're going to add one block again, which is going from top to bottom. And here, instead of upsampling, since we're going from bottom to top, we're going to perform downsampling. And we're going to have 5 convolutional blocks here. And we're going to perform a downsampling here by using one convolution. We're going to decrease the spatial size from 52 to 26, and this is a downsampling. And here we're going to concatenate the one coming from here with the previous layer of 26 by 26, and here we have an output feature map of 256, and we concatenate them together, and we have an output feature of 512. And we perform another downsampling after performing 5 convolutions. And the downsampling, after the downsampling, we're going to have a spatial dimension of 13 by 13, and we're going to use the one which is coming from after the spatial pyramid pooling, and we're going to concatenate them together because they have the same spatial dimension, and the output feature map of 512 is going to be summed together, and we have 1024. And then finally, after the concatenation operation and the convolution, after performing the CBL block 5 times, we're going to predict our first dense prediction will be here, our second prediction will be here, and our third prediction will be here. And this is referred to as the YOLOv4 head. And the YOLOv4 head is the same as the YOLOv3, and everything that we have discussed in the YOLOv3 applies also on the YOLOv4. And this represents all of the purple boxes. So in each case, we're going to predict 255. Will be the output number, which is going to be calculated by using this. So when we talked about the architecture of YOLOv4, we have mentioned we are introducing a new block known as CSP block, and we have seen the yellow boxes in the YOLOv4 architecture. All of the blue boxes are CSP blocks. And the CSP block in YOLOv4 architecture is only used in the backbone, and it's not used either in the neck or the head. And we need to pay attention to this point, because when we discuss about scaled YOLOv4 in the next video, we're going to introduce CSP in all of the blocks. So let's see in detail what the CSP block is doing. So in the first, before we have the CSP block, what we had was the original residual blocks. And you can see here we have the input, and we have a 3 by 3 convolution, and the feature map is 128, and we have a stride of 2. And inside the residual block, we have a 1 by 1 and 3 by 3 convolutions, and the output feature number is represented by 64 and 128. And we just take the input directly without performing any convolutions, and we sum it together with the output after performing these 2 convolutions. And the residual block is going to be performed 2 times. And on the original DarkNet 53, you can see that the number of parameters that we used can be calculated by using this formula. So we have a 1 by 1 and a 3 by 3 convolution, 1 times 1 and 3 times 3. And we have 64 and 128, which represents the feature map. And we sum them together, and then we multiply 2 times because we have 2 residual blocks. And the number of parameters for one residual blocks will be 2432. And we introduced CSP because we want to reduce the number of parameters. And when we reduce the number of parameters, we reduce the computation. And the intention of YOLOv4 originally was to make it run faster so that it could be deployed on embedded GPUs and CPUs for real-time object detection. So this is one CSP block, and they modify this residual block from Darknet 53 backbone of YOLOv3 to the CSP block, one block of CSP in YOLOv4. So the input will be the same. We have a 3 by 3 convolution. 128 will be the output feature map, and we have a stride of 2. But first, we divide this into 2. The first one will have 64 output feature maps, 64. The 128 will be divided into 2. And we perform a 1 by 1 convolution. And these two are going to be the same as the residual blocks here, but we modify the 128 here to 64 and 64, and the residual block is going to do the same thing as before. And then finally, on the output from the residual block, which is going to be performed 2 times on the first pass, we're going to perform another 1 by 1 convolution with 64 output features. And here we're going to have the first output. And the second one, we're not going to perform anything, and we're going to send it directly. And here we're going to perform concatenation of these two. And since we have 64 and 64 as the output, we're going to have an output feature map of 128. And the last one will be a 1 by 1 convolution. And then finally, when we calculate the number of parameters used in terms of one CSP block, the first term is going to show the 1 times 1 times 64 times 2 is the first convolution. This one and this one, we have 2 times. So this is going to represent the first term. And then finally, the second term is going to be the residual blocks. So we have a 1 by 1 and 3 by 3 convolution, and each of them have 64 output feature map. And since we have 2 of them, we're going to multiply by 2. And this will be the second term, and this represents the 2 residual blocks. And then finally, we have this block, and 1 times 1 times 64. And after the concatenation operation, we're going to perform the convolution one more time here. And we also multiply 1 by 1 by 128. And after we sum all of these together, we can see from the picture that we have 1,600 parameters, which is a significant reduction of the number of parameters when we compare to the original residual block that has 2,432 parameters. So the CSP has 2 advantages. The first one is reducing the number of parameters as we have seen here. And the second one is when we separate the input feature map into 2 and sending the first one directly after performing a residual block 2 times and performing the concatenation operation. This is going to aggregate feature maps from the previous layer, and it's going to preserve some of the information coming from the previous layer, and it's used for aggregation and aggregation of feature maps. and this is represented by the first dense block, and here we just have two partitions, and that's the only difference between the DenseNet and the CSP DenseNet. So this is just one of the CBMs. This is one of the CSPX, and the CPMs represents each of the convolutions for the yellow ones, and each of the convolutional blocks use a mesh activation function in case of YOLOv4. Finally, we have seen the SPP block in the YOLOv4 architecture, and we have said that we're going to perform a max pull operation of 5x5, 9x9, and 13x13. In the original SPP, if you have an output feature map from the backbone, you're going to divide it into a 4x4, which is going to be 16 representations, a 2x2, which are going to be 4 representations, and a 1x1, and you're going to select the maximum number from each of these grids. And since the feature map is going to have the channel number, and that dimension is going to be the same for each case, so that we can perform a concatenation operation. Then the 16s of 4 and 256 will be joined together. This was the original SPP used in FastRCNN, but in case of YOLOv4, a modified special pyramid pooling was performed, and instead of dividing in this manner, what they did was using a different 5x5 kernel with a stride of 1 on the feature map. So if the blue dot represents the feature map, the kernel, and we're going to select the maximum number by moving the kernel one step at a time, and one step at a time is represented by the stride number. For the first one, we use a kernel size of 5x5 for the blue dot, and for the second one, we use a kernel size of 9x9, and for the third one, we use 13x13. And once we have the representations from the 3 max pooling operations, we're going to concatenate them together, and you can see the output from each one will be 512, and when we concatenate them together, we're going to have 2048. So on the original YOLOv4 architecture, we have seen the SPP block after we zoom in, and here on the SPP block we have 512, and after the concatenation operation of each of the outputs, we're going to have 1024. The 512 and here will be concatenated together, and we have a total of 1024. And we have also seen the CSP block in detail, which is represented in this red box, and we have implemented the CSP only on the backbone. So that's all about the summary about the architecture of YOLOv3 and YOLOv4.